This last mini lecture today is going to be about buoyancy. The buoyant force is the net upward force on an object in a fluid. So imagine that we have a cylinder of water here. This is our little cylinder of water. Inside a beaker of water. And the water around the cylinder is holding up that little cylinder of water. So we've got our little kind of imaginary boundary around the cylinder of water. The water surrounding it is holding up that imaginary boundary for that cylinder of water. It provides, that surrounding water provides a net upward force equal to the weight of this little cylinder of water we can draw a boundary around. So when an object is immersed in a fluid, it displaces, meaning it pushes out of the way, the fluid that would otherwise fill that region of space. And this fluid that the object that is submerged is pushing out of the way, we call the displaced fluid. And this is Archimedes' principle. A fluid exerts an upward buoyant force on an object immersed in or floating on a liquid. The magnitude of this buoyant force equals the weight of the fluid displaced by the object. So every object that is in water, floating in water, submersed in water, it experiences this buoyant force. When you're in the bathtub, you experience this buoyant force. And this buoyant force is equal to the weight of the fluid that the body is displacing, or that the body is pushing out of the way. That's equal to the mass of the fluid displaced times gravity. That's also equal to, so we can rearrange the equation for density. Density is equal to mass over volume. We can rearrange that equation and solve it for mass. And the mass is also equal to the density of the fluid times the volume of the fluid. So we can say that the buoyant force is also equal to the density of the fluid times the volume of the fluid that's been displaced times gravity. There are three possible scenarios for objects experiencing buoyancy. The first is that you have a sinking object. An object will sink if it weighs more than the fluid it displaces. So in that case, the density of the object is much, much greater than the density of the fluid. So if your density of your object is greater than the density of the fluid, you will sink. If you drop something that's made of iron into water, it's going to sink because the density of iron is much, much greater than the density of water. An object will float if that object's density is much, much less than water. An object will, if you hold that object underneath the surface of a liquid and you let it go, the object will rise to the surface if it weighs less than the fluid it displaces, because it is experiencing a net upward buoyant force that's greater than the weight of the fluid it is displacing. And in that case, the average density of that object is less than the density of the fluid it's displacing. And finally, an object will remain motionless inside a liquid if it weighs exactly the same as the fluid it displaces. That also means that this object must have the same density as the fluid that it is displacing. And we call that neutral buoyancy, when the density of the object is the same as the density of the fluid it is displacing. And then it will just sort of hang out within the liquid without moving up or moving down. It's also the case that partially submerged objects in static equilibrium have a unique relationship. So if you are floating, let's say, a piece of wood on water, part of that piece of wood is going to be submerged under the water, and part of it is going to be above the water. And in that case, this is the case for an object that floats. And in that case, you can calculate the fraction of that object that is submerged just by taking the ratio of the density of that object that is floating to the density of the fluid that it is floating within. So the ratio of the volume of the fluid that is displaced to the volume of the object is equal to the density of the object that's floating divided by the density of the fluid that it is displacing.
we are going to apply Archimedes' principle to a partially submerged object. So here we have a raft constructed of wood with a density of 600 kilograms per meter cubed. Our raft has a surface area of 5.7 meters squared and a volume of 0.6 meters cubed. When the raft is placed in fresh water with a density of 1,000 kilograms cubed, to what depth h is the bottom of the raft submerged? So part of our raft is going to be underwater, part of it is going to be above water, and we are going to figure out how much of our raft is underwater. Okay, and we are going to do that. Well, we're going to at least find this height h that the raft is underwater. In order to do that, first we have to draw a free body diagram. So here's our raft, and we've got the weight of our raft downward, and we've got the buoyant force acting upward on our raft. Okay, and our raft is in equilibrium. It is floating, it's not accelerating up or down. So if we use Newton's second law on this situation, we've got the sum of the forces in the vertical direction equals the mass times the acceleration in the vertical direction. Okay, we're not accelerating, we're stationary, so this is 0. So 0 is going to equal our buoyant force upward minus the weight of our object downward. Maybe I'll put little O there for the mass of our object. So remember that the buoyant force is equal to the weight of the fluid that is being displaced by the object, but we can also write it as the density of our fluid displaced times the volume of our fluid that's displaced times gravity, and then that has to equal the mass of our object times gravity. Okay, so eventually we have to get this h here. Now I see that I can go ahead and get rid of g here, but I'm not told what the mass of my object is. I'm only given the density and the volume, but we can get it from the density and the volume. We know that density equals mass over volume. So if we solve this for mass, this tells us that mass is equal to volume times density. So the mass of our object is the same thing as the volume of our object times the density of our object. Okay, so we're told the volume of our object right here. We're told the density of our object right here. We know the density of the fluid that's being displaced. Okay, that's the water. But what about this volume of the fluid that's being displaced? Well, the volume of the fluid displaced is going to be the cross-sectional area of my raft times the height that's underwater. So the volume that's being displaced here is all of this part of my raft that is submerged underwater. So the volume of that part of the raft that is displacing the fluid is going to be this height here times the cross-sectional area of my raft. Here where I see the volume of my fluid displaced, then I can replace that with the area, cross-sectional area of my raft times h, the height that's going to be underwater. And then we just solve this equation for h. Okay, so remember that the volume of a cube or a rectangular prism is length times width times height. Okay, so that's our volume. We've got the area, which is the length times the width, and then we've got the height right here. Okay, so we solve this equation for h. H is then equal to the volume of my object times the density of my object divided by the density of the fluid, and we also have to divide by this cross-sectional area too. Okay, so this is my equation right here to get me the height of my my raft that is submerged underwater. Okay, so then this is going to equal the volume of my object, 0.6 meters cubed, divided by the cross-sectional area of it, which is 5.7 meters squared, times the density of my object, 600 kilograms per meter cubed. Divide that by the density of my fluid, 1,000 kilograms per meter cubed, and then taking care of this quantity here, turns out that this height that our raft is submerged underwater is 0.0632 meters. And then that's the same thing as 6.32 centimeters. So 6.32 centimeters of my raft is underwater. There's going to be some portion of it that's above water, has to be, because the density of my object is less than the density of water. Then let's think about how much, what fraction of my total raft is submerged underwater. And to find that, I can come over here. We've already derived essentially the equation we need. This part boxed in pink right here, I'm saying that the density of my fluid times the volume of the fluid displaced has to equal the volume of my object times the density of my object. Okay, we already derived that over here. Now, if I solve this for a ratio of the volume of my fluid displaced divided by the volume of the object, I will find that the volume of my fluid displaced divided by the volume of my object equals the density of my object divided by the density of the fluid. So what fraction of my raft is submerged underwater is going to be the same as taking the volume of my fluid displaced, which is the volume of my raft that's underwater, because that volume is what's pushing the water out of the way, and we divide that by the total volume of my object. That gives me the fraction that's underwater, and then that's equal to the density of my object divided by the density of the fluid. This only works for an object that's partially submerged, okay? And so then this only works for an object that has a density that's less than the fluid that it's floating in, okay? And then we find that this fraction of my raft that's underwater is going to equal our 600 kilograms per meter cubed divided by the 1,000 kilograms per meter cubed. And that tells me that 0.6 of my raft is underwater, or 60% of my raft is submerged. So 60% of my raft is submerged, and that's the same as having 6.32 centimeters of my raft underwater. You're also doing a similar thing for at-home lab 5 when you're finding the percent or the fraction of our ping pong ball sphere that's submerged underwater.
For this engagement check, I am going to ask you to answer these two questions now that we've talked a little bit more about buoyancy. Is the buoyant force on a solid lead, fully submerged object greater than, less than, or equal to the buoyant force acting on a solid iron object of the same dimension? And I'd also like for you to explain to me why you came to that conclusion. And to help you come to that conclusion, maybe to help you come to that conclusion, I also have a table here of the densities of lead, iron, and water. And then for your other question, how much of an iceberg is submerged beneath the ocean? Take the density quantities from the table over here for the density of ocean water and the density of ice. So I'd like for you to apply that relationship that we talked about between the volume of the fluid displaced and the volume of the object, and how that's related to the density of the fluid that's being displaced and the density of the object. So looking at that ratio for objects that float in liquids, you can figure out what is the fraction of an object that is submerged in a liquid if you know the densities of both of those liquids.